Welcome everybody to a new day of Advent of Code. Yesterday was so far the hardest day for me. I think it took me like 50 minutes to do part 1 and then another 2 hours to mess up part 2. But at some point VS Code removed my code, so I don't have a recording of that left. But we are out with elephants! You've emerged near the base of a large volcano. Seems to be actually erupting. Lava seems to be flowing away from you and towards the ocean. Depending on the specific compounds in lava and the speed at which it cools, it might be forming obsidian. And the cooling rate should be based on the surface area of the lava droplets. The lava is moving, the scan is very good, its resolution is quite low, and as a result it approximates the shape of the lava droplet with 1 × 1 × 1 cubes on the 3D grids. Count the number of sides of each cube that are not immediately connected to another cube. After counting up all the sides that are not connected, this total surface area is 64. Day 18.txt. Let's also immediately take this here. How many lines do we actually have? $20,000. Okay, so let's see. The cooling rate should be based on the surface area of the lava droplets. So we get the shape of the lava droplet with 1 × 1 × 1 cubes. So if my scan were 1 1 1 2 1 1, each cube would have a single side covered and 5 sides exposed. After counting up all the sides that are not connected to another cube. Okay, so if I have 1 2 2 and 2 2 2, one side is not connected to another one. Let's see, how do we represent this? Let's see. How does this work? Let me paint on the whiteboard. Already getting flashbacks to that puzzle last year where you had to kind of get overlapping squares. But so in this case, if I would have these 3 things, then this side is connected. I guess that in this case we can just do this super exhaustively. That wouldn't even be too bad. Oh, that would actually be quite easy. So we can just go over each cube and see if it's connected to any other cube. Like it's just helps for. Oh, actually, why not just use immediate indexing? Ha! It is time. People who watch more of my videos know what time it is. From collections, import a default dict. Perfect. Connected sites is 0. No, that's, they say connected sites is 0. Let's say the, I don't know, cubes is D for dict. For line in lines. So it's x, y, z is int x for x in line split. Cubes is true. That gives us these cubes. Perfect. So we have our dotas is a list with x minus 1 make a list with all the neighbors of a cube for each side. There we go. Okay, so all right, x plus dx, y plus dy. Cooling sites. Print the cooling side 64, and then we do this for our input. All right, 904 on this today's leaderboard. That seems pretty okay. The cooling rate depends on the exterior surface area, but your calculation also includes the surface area of air pockets trapped inside the lava droplets. Consider the only cubes that could be reached by water and steam as lava droplet tumbles into the pond. Okay, how do we do that? So we can have air pockets. The question is, how big can these things be? Because it's possible that you have like a massive air pocket, right? So in this example, they only have one tiny pocket. What is the surface area of your scanned lava droplets? Let's see, what approach do we want to take? How do we know if something is trapped? What does it mean if something is trapped? I guess we could simply do a breadth first search again. Or do some flood filling. I'm now thinking about just building a okay. Let's see, fields pockets is set. We don't even need a default text. I'm kind of disappointed. Let's see if this still gives us the same result. If yeah, okay. So let's get rid of the default text because we don't need it. Even though I'm very disappointed about that. I'm happy that we have an easy first thing. So then we can say what I'm thinking about is simply making a breadth first search and assuming that pockets have a maximum size and just kind of keep expanding a pocket until you reach the maximum depth. And I guess in this case, the worst case would be something where we have 1,000 on a row and then like one line of air pocket and then another 1,000 on a row. But I guess that's not the case. So let's assume that we're dealing with an average case here and not the worst case. Oh, it can't even be like that. It has to be... Okay. Anyways. Let's see. Let me again go over part 1, cooling sites. Okay. New place is this. So what I would like to do is go deeper and keep it deeper and deeper, like with a frontier, like for a search frontier. If there is nothing remaining, then it has to be an air pocket, and then everything I had so far has to be added. So what I can do is create breadth first search pockets with like my start. And what I probably want to do is have a tuple between the depth and like depth and position. I learned that .pop0 is apparently, according to Peter Norvig, ON, so that's not good. So I should use heaps here, but let's skip it for now. And then we can also say max depth, I don't know. Start with, I don't know, 10. We can say if current 0 is larger than max depth. This is not an air pocket. Return false and the visited places. Then we can say for while q.pop then we know for sure that it is not an air pocket. Known outside, known lava, and known outside. Square. If we already visited that, no need. If the square is in, go away. If the square is in our amount of known lava, we can continue. So if we are either too far or the square is in known outside, if we already know it's air, like we don't have to keep searching. Okay, otherwise we take all the neighbors. We can say known outside is a set. We have our filled pockets. If the news place not in filled pocket and new places not in known outside. We can say is here we can return true in the places we visited. And then of course we can say is air pockets breadth first search. Is pockets visit this air pockets. So we get a new place. Our current field pockets are known outside. It is a pocket. I guess dot update ads, right? Yeah, perfect. Okay. I wonder how long this is going to run. So now we have okay, let's first do the following thing and run this example again, because we know that this how many do we have here? We have 13, right? Print known inside known trapped 14. Okay, so we apparently find this one pocket, which is good. Yeah, which is good. And then if we want to do this again, we can just copy paste this and say sites. Yeah, there's 5.8, that's good. Okay, and now comes the question, how deep should we make our depth first search, right? Three, 2, 1, 0. Yeah, this is 2018. This is a bit stupid because, of course, the deeper we go, the longer it will take to run. And I guess we found an answer because it's not changing. Rank 617. All right. That's pretty good. I'm happy with today's performance because we got on the top 1000 twice again. What am I not happy by? The code is very ugly because we copy-pasted things multiple times. I'm sad, of course, that we are not using a default dict. I'm happy that we managed to find a relatively efficient breadth first search algorithm. I'm sad that we didn't do any searching for what a good maximum depth is, but that's also fine. I can update that later. And the code is relatively ugly, but the sets are cool. Like, doesn't take that much. I guess the memory is relatively big, so if the input was way bigger, we would have a massive issue. I'm happy that we could represent everything as voxels and we didn't have to create massive squares and try merging them or something. Like last year, there was this one day which was terrible. But yeah, overall, good day. And have a good day.